Today, let's look at our free response question number 092B. We are allowed to use a calculator. In fact, it's required to use a graphing calculator on this problem. So a storm washed sand from a beach, causing the edge of the water to get closer to a nearby road. The rate at which the distance between the road and the edge of the water was changing during the storm is modeled by f of t, which happens to be the square root of t plus cosine t minus 3. That's meters per hour. So this function is actually already a derivative, right? It says it's a rate. T is measured in hours since the storm began, or after the storm began. So that's important to know also. The edge of the water is 35 meters from the road when the storm began, and the storm lasted 5 hours. Then they're actually telling us the derivative of f prime, or the derivative of f, which is f prime, and that's 1 over 2 squared of t minus sine t. We could have figured that out on our own, but it's nice that they gave it to us. Now, one thing I want to point out to you is that they did give us a closed interval for this particular function. The storm began and lasted 5 hours. So t is on the interval 0, 5. Okay, so we're going to attack each one of these parts. There's 4 parts here. We'll do one on each slide. So for part A, we are asked to find the distance between the road and the edge of the water at the end of the storm. So after 5 hours, we want to know how far away things are. We are given a rate which is measured in meters per hour, right? That's this thing. So that's a rate. If you want to find out the distance given a rate, you have to do an accumulation function. So for us, let's call this D. D is going to be, what do we start with? It started out 35 meters away. So that's our initial condition. We got to make sure we incorporate that into our equation. And then we're accumulating change over the course of 5 hours. So we have to build an accumulation function or expression. We're going to integrate from 0 to 5 this function f of t, which is the square root of t plus cosine t minus 3. And together, the 35 that we started with plus the change that we accumulate over the course of 5 hours, that'll give us the distance between the road and the edge of the water at the end of the storm. And we're allowed to use a graphing calculator, so what I've done is I've just typed this expression into my graphing calculator, and then I'll round it off to 3 decimal places, and this came out to be 26.495 meters. So roughly speaking, we lost about 8.505 meters of distance. We're actually closer than we used to be. We started at 35, now we're at 26.495. And that's a classic example of just using accumulation to solve an initial value problem. So that part wasn't too bad. We'll attack part B on the next slide. Part B asks us to use correct units. Using correct units, interpret the value f prime of 4 equals 1.007 in terms of distance between the road and the edge of the water. So this act of interpreting is something that not all math students like to mess with. But we'll see if we can break this thing down. So first of all, let's just write the expression down, and we'll see if we can figure out what each part is. So we've got f prime. We're plugging in a number 4, and what's popping out is 1.007. I'm just sort of making each of these pieces a little bit different colors so we can see how they fit together. So remember, f prime is the derivative of a rate. So it's kind of like an acceleration, and essentially it's the second derivative. And so that'll affect our units. F prime receives hours. So this t, this 4, is the number of hours. And this output, 1.007, is the derivative of F. F was already meters per hour, so this is meters per hour per hour. We usually call that meters per hour squared. So basically what this is saying is after 4 hours, I'll just write this out in as short as I can. After 4 hours, the distance is changing. The rate at which the distance is changing is increasing at a rate of, let's see, how do I want to say this? Under normal circumstances, I'd start this video over, but what the heck, let's just make sure we're saying this correctly. So what we're saying is that the edge, the distance between the road and the edge of the water, I'm just going to call that the distance, is changing. Spell that correctly, dude. Is changing at a rate of, this is 1.007 meters per hour squared. Okay, so that sentence essentially just says what I already wrote above in more concise terms, that we covered 4 hours, and at the time, right at 4 hours, our thing is changing, accelerating, if you will, at 1.007 meters per hour squared. And I think we've covered everything they asked us to cover. They wanted us to use correct units. We've done that, and we interpret it in terms of the distance. We did that. So I think that'll suffice for that problem. We're basically taking this expression f prime of 4 equals 1.07, and we're explaining what it means. Let's tackle part C on the next slide. Let's look at part C. Part C says, at what time during the 5 hours, at what time, let's make sure we underline that because that's telling us what we want to find. At what time during the 5 hours of the storm was the distance between the road and the edge of the water decreasing most rapidly? There's a bunch of English going on there. The function f tells us when the distance is increasing or decreasing. But when it says most rapidly, it really means we want to find out how f is changing. So we want to find essentially an absolute minimum, the most negative value for f. To do that, we have to take the derivative of f, which we've already been given, and we have to find its zeros. So here's my f prime of t. It is 1 over 2 square root of t minus sine of t, and I need to find the critical points, right? So essentially we need to set this thing equal to 0. Okay, you can use your graphing calculator to do that. You simply enter this function and then use the, there's a 0 function on your graphing calculator, or you can look to see where this thing crosses the x-axis and then use the intersection function or the 0 function. So decide how you want to do that. I've already done it, and I came up with 2 places. I came up with t equals 0.66187 and t equals 2.84038. I'm keeping all the decimals for now. When we write our final answer, we'll round it off to 3 decimal places. And remember, I mentioned on the other slide that we are on a closed interval from 0 to 5, right, over the first 5 hours. So we are essentially trying to find an absolute minimum on this closed interval. The extreme value theorem, I don't know if you remember that one or not, but that's an EVT, right? That's what we've been calling it, says that we have to be able to find an absolute extreme, right? An absolute min and an absolute max on a closed interval for a continuous function. So we should be able to do that here. Notice we have an undefined value at 0, but that's also an endpoint. So we're going to test that one anyway. So we're going to test 4 values in f, and you'll have to use your graphing calculator to do this. We need to compute f of 0, f of 0.66187, f of 2.84038, and f of 5. I know I'm writing this funny because I want to get this color in here. We have to get these four function values, excuse me. That's how you find the absolute extremes on a closed interval. You find the critical points and the end points, and you compute the y values. In our case, the lowest one, the most negative, is going to be the one that we want. And of course, I've already typed these in on my calculator. When I plugged 0 into f, I got -2. When I plugged in 0.66187, my value was -1.39760. When I plugged in 2.84038, that value was -2.26963. And when I plugged in 5, I got -0.48027. Now, it might be a good time to pause the video and double check my calculations. You never know when you're going to make a mistake, but I think I've got this thing nailed. And I notice here that the minimum, or the lowest number, is -2.26963. That is when this thing is decreasing most rapidly. And it occurs at 2.840 hours. So in terms of my answer, remember it says at what time during the 5 hours? I was asked to find a time, and my time is, I'm going to round off to 3 decimals, 2.840 hours. So I had to use a little bit of interpretation here to figure out what kind of math to do. When it said decreasing most rapidly, it meant that I wanted to find out the extreme values of the function f. And the way you do that is you take f prime, you get your critical points, you test your endpoints and your critical points. And in our case, the minimum occurred at, almost 3 hours. Right there. Okay, that was a short problem in terms of stating it, but we had to really do some interpreting to figure out what they wanted and then apply all kinds of cool calculus to do that, specifically the extreme value theorem, which of course is one of my favorites. We'll tack part D here on the last slide and we'll be done with this thing. If you've read part D, you already know that there's not any calculating to go on here. I'm going to read it through and then we'll talk about what it's asking us to do. After the storm, a machine pumped sand back onto the beach so that the distance between the road and the edge of the water was growing at a rate of g of p meters per day. Notice they switched from hours to days on us. P is the number of days since the pumping began. We're supposed to write an equation. So that's what this problem's asking us to do. We're not producing a value for an answer. We're producing an equation. Write an equation involving an integral expression whose solution would give the number of days that the sand must be pumped to restore the original distance between the road and the edge of the water. The original distance, if you'll recall, was 35 meters. We want to make sure we get back to 35 meters. Restore the original distance. Okay, so we already know how much it changed over 5 hours. It was 35 plus that definite integral from 0 to 5 over f of t, right? Remember when we did that? Ended up being 26 point something. So we lost about 8.505 meters of beach. We want to undo that. So over the 5 hours, we accumulated change of 0 to 5 of f of t dt. We said that was approximately negative 8.505, right? We lost 8.5 meters of beach over those 5 hours. That's how our answer ended up being 26 when we started at 35. We want to reverse that change. So whatever we do with this pump has to add up to the opposite of negative 8.505. So our new, our pump, this G, right, is going to produce a total of 8.505 meters of change. And we don't know how long it's going to take to get there. We don't know how many days. That's what we're trying to find. So I'm just going to call the number of days D. Oh, baby. You didn't see that, but a little message came on my screen. Maybe you did. I don't know. D is the days the pump runs. Okay. So if I want to run this pump for a certain number of days, and I'm writing an integral expression. This is an accumulation. So I'm going to start my clock. My clock starts at 0. I'm going to run for D days, and I'm going to integrate the change, right? The rate at which the pump thing pops out sand, which is written something like this. And then the way we're going to solve for D is to make, we're going to solve and set it equal to the opposite of this 8.505. It said write an integral expression, so I'm going to write the integral instead, but essentially we need the opposite of that 8.5 meters, or negative 8.5 meters. We need positive 8.5 meters. So this expression will get us there. And just for emphasis, let me make this D a different color, because that's the thing we're going to solve for. If we were to solve, right? They didn't ask us to do that. They said write an equation which has an integral expression, and that's what we did. Let me just make sure this thing looks right. I'm going to start running the pump, and I'm going to accumulate the change, right? G of P is a rate, so if I integrate the rate, I'll get the amount of sand. I don't know how long I'm going to run that pump, but I know I'm going to stop when I get back to where I started. We started at 35, and the way we undo the change is do the opposite of the change. And so, yes, this does accomplish what we were asked to accomplish. So that's great news. I'm going to highlight that bad boy and call it good. So this whole AP problem here, number 092B, really had a couple of different parts, Part A and Part D, where we had to use accumulation. In the middle, we were doing a lot of interpreting. And so, we've got to get used to doing this. Calculus is not all just cranking out derivatives and integrals. Applying what we've learned is really what we need to practice here over the next period of time here, month or so. Anyway, good luck, good work on this thing, and keep me posted on your progress.